This is another example involving the application of the Coulomb's law. So at this point, if you like, you can pause the video and try out the question by yourself. So let's read the question. 11 point charges are placed on two concentric circles as shown in this figure. The radius of the outer circle is twice the radius of the inner circle. So if we consider the radius of the inner circle as r, then the radius of the outer circle would be twice that value, 2r. If a plus q charge is placed at the center of this concentric circle, so somewhere here we are going to place a plus q charge, we want to find the magnitude of the net electric force acting on that charge due to all these 11 point charges, as well as the direction of that net electric force relative to the positive x-axis. Now, if we define our coordinate system, I'm going to define the horizontal right-hand direction as our plus x or positive x direction, and vertically upward direction as our positive y direction. So with this in mind, let's try to figure out the answer for this problem. First, I'm going to use symmetry to simplify this problem. If you consider the origin relative to the center or the origin, which is over here at O, look at the positioning of the charges that are represented in blue. These are the charges, 8 charges that are on the outer circumference or the outer circle. You can see relative to the origin, they are symmetric. If you think about the vertical direction, there's a plus 4q charge, 2r distance upward, and 2r distance in the downward direction. Then 7q to the left and 7q to the right. 2q, minus 2q over here and minus 2q over here. Minus 2q on this side and minus 2q on this side. So relative to the origin, the point charge distribution along the outer circle is symmetric. As a result, we can conclude that those 8 charges, the net electric field due to those 8 charges at the charge on the center is 0. Okay, so I'll just show you for one pair because we have 1, 2, 3, 4 pairs. I'll just consider this plus 4q and the plus 4q charge that are vertical. So this is our plus q charge at the center, and in an upward direction we have the plus 4q charge that is 2r distance away, and then the other 4q charge, again that is 2r distance in the downward direction, plus 4q. Now let's look at the forces acting on this center particle, center charge, due to these two plus 4q charges. I'm going to represent the forces by a different color so that it's more clear to you guys. So these two charges are equal sign. So there's a repulsive force. This 4q will exert a repulsive force on this charge at the center. Similarly, this 4q is going to exert a repulsive force in the downward direction like this. Now these two forces will cancel out with one another. You should be able to write down the magnitude of that force from Coulomb's law. K Q times 4q. Remember, I'm just writing the magnitudes. We are dropping the signs when we write the magnitude of the Coulomb force, divided by the separation squared, 2r squared. So there's this magnitude in the upward direction and the same magnitude in the downward direction. You have two opposite vectors, they will cancel out. As a result, there's no contribution for the electric force at the central particle from these two charges. In a similar way, we can conclude that the minus 2q charge here and the minus 2q charge over here, the electrostatic influence that they are going to make at the central charge is 0. Similarly, the minus 7q over there and the minus 7q over here, their repulsive forces on the central particle will cancel out with one another. Similarly, these two charges, minus 2q and minus 2q, they will have electrostatic forces at the central particle, but they are going to cancel out. So simply, you can think from symmetry's sake, looking at the center, you can say that they are the net electrostatic force due to the 8 charges that are in the outer circle is 0. So to summarize this important point, from symmetry, the net force on the positive Q charge at the center O due to the 8 charges on the outer circle is 0. Now let's look at the electrostatic forces acting on the particle at the center due to the 3 particles on the inner circle. Now let's look at the forces acting on the particle placed at the origin due to the 3 charges on the smaller circle. So I'm going to here draw the plus Q charge that is at the center. So particle at the center, particle at the center. First, I'm going to start with this charge plus Q charge on the left hand side of the particle at the center. You can see that's plus. The particle at the center is also positive. So this will exert a repulsive force, that is a force along the plus positive x direction. So I'm going to draw that force like this, and let me call that F. Similarly, you can see there's a negative Q charge on the right hand side of this particle at the center. That's going to attract, that's going to exert an attractive force on the particle at the origin. And you can see it's the same magnitude. The distances are the same, the charges are also the same. Only their polarity changes. So it's going to attract, and then that force is also in the same direction like that, and I can call that F. Now let's look at the force exerted by the plus 2q charge. You can see that's also going to exert a repulsive force on the particle at the center, but this time the repulsive force is in the negative y direction, and you can see that it's twice the force exerted by each of these plus q charges. So as a result, I can show that force as 2F. So then further simplifying this vector diagram, I'll have 2F here to the in the positive x direction and 2F along the negative y direction, where F can be obtained, it's a magnitude of a force, it can be obtained using Coulomb's law, and we can see that F is K, magnitude of Q over R squared, right? So the 2F force, you can see this 2F force is K Q. Instead of this Q, we apply the 2Q, and that's why it becomes 2F, because the charge, one of these charges, is twice the value of the other charges. So F is given like this, and if you like, you can replace K by 1 over 4 pi epsilon naught. So then I can simplify this further, Q squared. I'm just looking at the magnitudes, and then instead of K, I can write 1 over 4 pi epsilon naught, where epsilon naught is the permeability of free space, unless given by default, we consider that the charges are placed in free space. So that's why I'm simply writing 4 pi epsilon naught and then r squared. But we are not done yet. We need to find the magnitude of the net force. So let me show the net force using a different color. Let's say that the net force goes like that, and I'll call it F net. And let's say that it makes an angle theta with the positive x-axis, and it's pretty much obvious to you that it's symmetric, and this angle, if this is 90 degrees, this angle should make 45 degrees. But let's show that. Nonetheless, we'll show that. So net force, magnitude of the net force, F net, is given by, you can see these two forces are perpendicular to one another. So I am simply applying the Pythagorean theorem here. I can write 2f squared plus 2f squared. Okay, so that's going to give me the net force. And when we do the simplification, try it out, then symbolically I'm going to express this: 2 times square root of 2 times F is the net force, the magnitude of the net force. And then I can substitute for F this quantity, because there are no numerical values given. So then I can simply substitute 2 square root of 2 Q squared over 4 pi epsilon naught R squared. Okay, so that gives me the magnitude of the net force acting on the plus Q charge particle that is placed at the center of this concentric circle system. Now the direction, so let me write down magnitude. But now let's find out then the direction would be, because we need two things to completely describe a vector: size and the direction. Then the direction from the positive x-axis in a counterclockwise direction. So I'm going to write that in a counterclockwise direction. In a counterclockwise direction, you can see that's in this direction. So I mean, if we are measuring, this is our positive, you can see that that's our positive x-axis. So I'm going to measure the angle in this direction, counterclockwise. Okay, so that would be simply 2 pi minus theta. Okay, so my objective is to find theta, but you can see that theta is pretty straightforward. Theta can be obtained by inverse tangent y component, which is 2f, over the x component, which is again 2f. So then you get inverse tangent 1, which is nothing but pi over 4, or in degrees, this is radians, that would be 45 degrees. And you can convince yourself these two forces are perpendicular to one another and they're symmetric. So then the net force should go along a bisector, an angle bisector. It should bisect the angle between the two original forces. So the angle between the two original forces is 90 degrees. Bisecting means it goes like 45 degrees with each force. So then this is like, you can write it as 2 pi minus pi over 4, or in other words, like let's say 360 degrees minus 45, so that would mean 315 degrees. So that's how you do this problem.